How can this work at impossible scale? 10,000 feet below the Gulf of Mexico's surface, beneath layers of sediment laid down over millions of years. Pressurized crude oil waits in porous limestone formations. But getting to these deposits requires one of the most complex industrial operations on Earth, a precisely choreographed sequence that begins with surveying empty ocean and ends with crude flowing through underwater pipelines to refineries across the nation. The process starts with lease block surveys, where specialized vessels drag seismic equipment across predetermined grid patterns. Sound waves penetrate the seafloor, bouncing back from rock formations to create three-dimensional maps of potential oil reservoirs. These surveys can take months, with crews analyzing returning echoes to identify the telltale signatures of hydrocarbon deposits trapped in anticlines and fault blocks. Each lease block covers roughly 9 square miles of ocean floor, about the size of Manhattan, and companies bid millions of dollars for drilling rights based on seismic data alone. Once a promising site is identified, the real engineering challenge begins. Semi-submersible drilling rigs, floating platforms the size of city blocks, position themselves above the target coordinates using dynamic positioning systems and GPS satellites. These rigs must maintain their exact location despite ocean currents, wind, and waves that can reach 40 feet during Gulf storms. The drilling process starts with a conductor pipe driven into the seafloor, followed by progressively smaller diameter pipes that telescope down through layers of sediment, salt domes, and rock. Creating the wellbore itself demands extraordinary precision. The drill bit, spinning at the end of a string that can extend 3 miles down, must navigate through different geological formations while maintaining wellbore integrity. To put this in perspective, it's like threading a needle from the top of the Empire State Building while the building sways in the wind. Drilling mud, a carefully formulated mixture of water, clay, and chemical additives, circulates continuously down through the drill pipe and back up the wellbore annulus. This mud serves 3 critical functions. It cools the drill bit, carries rock cuttings to the surface, and most importantly, maintains pressure balance to prevent uncontrolled hydrocarbon releases. At the ocean floor, where crushing water pressure exceeds 4,000 pounds per square inch, enough to implode a steel drum instantly, engineers install the blowout preventer. This 40-foot-tall, 300-ton assembly represents the primary safety barrier between the high-pressure oil reservoir and the ocean above. Connected to the drilling rig by a marine riser system, the BOP can slice through drill pipe, seal around it, or completely close off the well, using blind shear rams with enough force to cut through steel like butter. Once the well reaches the oil-bearing formation, completion engineers install the subsea tree, the underwater equivalent of a traditional wellhead. This Christmas tree-shaped assembly of valves and fittings controls oil flow from the reservoir and connects to a network of flow lines and risers that transport the crude to the surface. The subsea tree must withstand not only the immense water pressure at 10,000 feet, but also the corrosive effects of salt water and the high-pressure, high-temperature conditions of the oil reservoir itself. A single valve failure here can mean the difference between controlled production and environmental disaster. The pathway from seafloor to surface involves a complex system of risers, large diameter pipes that carry oil, gas, and produced water up through the water column. These flexible or rigid pipes must bend and flex with ocean currents, while maintaining structural integrity under internal pressures that can exceed 5,000 pounds per square inch. Steel catenary risers hang in lazy S-curves from floating production platforms. Their shape calculated to minimize stress as the platform moves with wave action. When hurricane-force currents hit these risers, they can flex up to 30 feet from their normal position. At the surface, floating production platforms, some weighing over 100,000 tons, serve as industrial cities in the middle of the ocean. These vessels, whether converted tankers or purpose-built facilities, house the separation equipment that splits the well stream into crude oil, natural gas, and produced water. Gas turbines generate electricity for the platform, while flare stacks burn off excess gas that cannot be captured. Living quarters accommodate crews of 150 to 200 workers, who rotate on and off the platform by helicopter on 14-day shifts. Everything these workers need, from fresh water to spare parts weighing several tons, must be helicoptered or shipped to the platform. The separated crude oil flows through export pipelines that snake across the Gulf floor toward shore terminals. These pipelines, some stretching over 200 miles, must navigate underwater canyons, cross shipping channels, and withstand hurricane-force currents. Pig launchers and receivers allow maintenance crews to send cleaning and inspection devices through the pipes, while pressure monitoring stations detect leaks that could release thousands of barrels into the marine environment. A single major pipeline can carry 400,000 barrels per day, enough to fill an Olympic swimming pool every 2 hours. The entire system operates as an integrated network, where failure at any point can shut down production worth millions of dollars per day. Hurricane evacuations require crews to safely shut in wells and disconnect risers, a process that can take 18 hours of precise coordination. Equipment failures 2 miles underwater demand intervention by remotely operated vehicles equipped with manipulator arms and cutting tools, essentially underwater robots performing surgery in crushing darkness. Each well can produce for 20 years or more, but maintaining flow requires constant management of reservoir pressure, water injection, and artificial lift systems that help push oil to the surface as natural reservoir pressure declines. The important detail is that how America pumps oil from 10,000 feet below the Gulf is not one machine. It is a chain of physical constraints that must work together. The real sequence is unforgiving: lease block survey, offshore drilling rig and wellbore, blowout preventer and subsea tree, risers and flow lines, floating production platform, pipeline export terminal, and final verification. That chain creates a narrow margin. Materials, labor, schedule, power, cooling, transport, and inspection all have to arrive in the correct order. A delay in one hidden subsystem can make the most visible structure look finished, while the project is still technically incomplete. This is why the engineering story is not only about scale, but about coordination under pressure. For energy infrastructure, the hidden problem is reliability. Generation, transmission, protection systems, storage, and control rooms must react before a failure spreads. The visible machines are only part of the system. The real value is the ability to keep power moving when demand spikes or equipment fails. Transformers, turbines, breakers, pipelines, and substations become national infrastructure because there is no simple substitute when they are missing. That makes the project a test of manufacturing capacity as much as engineering design. The key question is whether the system can keep performing after the cameras leave and real demand begins. That is the difference between a spectacular build and infrastructure that actually changes national capacity. And that is why the final test is not construction alone, but whether the entire system can operate under pressure. The important detail is that how America pumps oil from 10,000 feet below the Gulf is not one machine. It is a chain of physical constraints that must work together. The real sequence is unforgiving: lease block survey, offshore drilling rig and wellbore, blowout preventer and subsea tree, risers and flow lines, floating production platform, pipeline export terminal, and final verification. That chain creates a narrow margin. Materials, labor, schedule, power, cooling, transport, and inspection all have to arrive in the correct order. What remains hidden in this vast underwater industrial landscape is just how much untapped oil lies beneath formations that current technology cannot yet reach economically.